Energy can be changed into other forms, and that's a fundamental part of the machines around us. Today we're going to look at how chemical can be changed into electrical, into thermal, into kinetic, and then into electromagnetic, all in order to take a photo. We're going to have a look at how X-ray machines work. It starts with thermionic emission, heating a metal filament to produce a cloud of electrons. These electrons, this cloud of electrons, is then attracted towards a metal anode, which is positively charged. The negatively charged electrons are accelerated towards the positively charged anode, completing a circuit. Now, here's the bright idea. The electron has kinetic energy. What if we find a way to convert that kinetic energy into light energy? We want the electron's kinetic energy to become a photon of electromagnetic radiation. To try, we're going to accelerate an electron across a potential difference of 30,000 volts, 30 kilovolts. The electron has a charge of minus 1.6 times 10 to the minus 19 coulombs, so the energy is given by work done, W equals QV, equals 1.6 times 10 to the minus 19 times 30,000, which is 5 times 10 to the minus 15 joules. Alright, so I'm not really worried about the sign here because we're dealing with work done, and the sign simply shows which direction the energy is flowing, but that's a separate topic. For now, that energy is going to be released as a single photon. We'll come back to how that happens, but for now, let's assume that's true. 5 times 10 to the minus 15 joules is going into one photon. So since E equals HF, and hence E equals HC over lambda, rearranging that to lambda equals HC over E, that's 6.63 times 10 to the minus 34 times 3 times 10 to the 8 over 5 times 10 to the minus 15, which comes to 4 times 10 to the minus 11 meters. That's the wavelength of an X-ray. So now we know that using a reasonably small 30 kilovolts, we can get up to about 5 kilovolts in a school lab. So reasonably small 30 kilovolts, we can generate the right amount of energy to get an X-ray photon. The next problem to be solved is how to get that photon. The obvious way to get the kinetic energy of the electron into another form is to stop the electron. And that's exactly what we're going to do. Quite simply, we let the electron hit the anode and come to a stop. Kinetic energy goes from 5 times 10 to the minus 15 joules to 0 joules. And that energy goes somewhere. Now, there may be many things that can happen, but one of them is this. When a charge is accelerated, when it changes velocity, it changes energy. On a quantum level, changes in energy involve photons. Photons carry energy into and out of systems. If you want to dig into that some more, go and learn about magnetic fields. But for now, let's just accept that changes in energy involve photons. So, accelerating an electron will involve a photon. Slowing down an electron will release energy, so release a photon. If the electron is stopped in one quick exchange, a photon with 5 times 10 to the minus 15 joules is released. But if the electron bounces around a bit or gets deflected, the kinetic energy will be lost in steps, with each step releasing one photon. Let's do a quick recap. We heat up a metal and release electrons using thermionic emission. Those electrons are accelerated towards an anode. They decelerate and release their energy in the form of photons. The photons have a range of energies because the electrons do not lose all their energy in one go. So, if we plot the energy of the photon being released against how often a photon with that energy is released, we'll get something looking like this. Sometimes all the energy will be released at once, but this is actually quite rare. More often, a deflection will happen, and again maybe, and so we get a whole bunch of different energies. This is the basic pattern, with a peak for the most frequent, a long tail tending towards zero energy and zero frequency, and a sudden drop to zero frequency here, where all the energy is converted to a single photon. There can't be any photons with more energy, since a quantum event like creating this photon can only involve a single electron, and the electron cannot have more energy than this. So this is the maximum energy of a single electron, giving us the maximum energy of a single photon. Flipping this around, we normally plot the graph with wavelength on the x-axis. Since E equals hf equals hc over lambda, increasing energy means decreasing wavelength. So the graph is flipped on the x-axis. Now we have a graph with a minimum wavelength. So in summary, we have heated up a wire to release electrons, then accelerated them through around 30,000 volts towards a target. As they approach or hit the anode, they decelerate and release photons with a range of wavelengths from this minimum here to a long tail. There's one final addition to this graph. Sometimes the electron comes in and hits the atom, resulting in an excited electron. Maybe it knocked it up a level, or maybe it got absorbed. Whichever way, the excited electron will, at some point, relax and release its energy. Since this can only release photons at specific wavelengths, we get characteristic peaks on the graph. The final graph is a curve for the background radiation with characteristic peaks that depend on the material we are using. This gives us a source for X-rays, and what we're going to do next is see if we can form a beam that we're going to be able to use for imaging in the X-ray machine.